Okay, so starting video 2, let's start to look at neural networks and what we need in order to build one. So essentially we have the simplest neural network with an input layer, one hidden layer of hidden units, and an output layer. I've exemplified this with 2 inputs, 2 outputs, and 3 hidden units in one hidden layer. This is very, very simple. So essentially what we need is, you can see that all of the nodes in the input are connected to all of the nodes in the hidden layer, and all of the nodes in the output are connected to all of the nodes in the hidden layer. So this is a fully connected neural network. And that's what we're going to show and assume going forward, that all of the nodes at one level are connected to all of the nodes at the level above and the level below. So this is fully connected here. And essentially what we need to start off with is a vector of input nodes, a vector of hidden nodes, and a vector of output nodes. Okay, and then we have, for each of the connections between a node at one level and a node at the next level, we have a series of weighted connections. So each of the arcs in the network has a weight. So we have an input of a vector of input nodes, a vector of hidden nodes, and then maybe multiple vectors of multiple hidden units at different hidden layers, and a vector of output nodes. A matrix of weights connecting the input nodes and the hidden nodes. And you can see that that has dimensionality of 6 because there are 3 nodes in the hidden layer and 2 in the input layer. And then we have another 6, 3 by 2 matrix of weights connecting the hidden nodes and the output nodes. We train a neural net by iteratively updating the weights. We start by randomly assigning weights to each edge, and then we percolate back the error, if we're using an error metric, via back propagation to adjust the weights so that we then retest on the same input test set, and hopefully we get better performance, and we keep going until we can't get any better improvement from the neural net on our test data. Once we have that, we freeze the neural network, and then we can apply it to new test data. So I'll leave you guys to go through these next few slides yourselves. Essentially, this is exactly what we saw earlier on. We have a set of weighted inputs. We add those up. We apply the sigmoid threshold function, and we get an output of between 0 and 1. Here's a worked example, but I'll leave you to go through that. It's fairly self-explanatory. If anybody has a problem, we can go through that in the Q&A session next week. But again, you can see, even for a small network, we have lots and lots of these calculations. Many millions or even billions in a sort of state-of-the-art network. But essentially, all we have are 2 sort of well-understood mathematical concepts of vectors and matrices, and the most difficult part of neural networks is matrix multiplication, which is not terribly difficult, and there are a range of tools around today which do that very fast. We limit the size of the matrices. We limit the size in translation. We limit the size of the vocabulary to, let's say, 20K or 30K or 50K, in order to make sure that the matrices don't become too large and the calculations become unfathomable. It just would take far too long to actually work out what the answers might be. So essentially, we're going to deal with input. We're going to apply some sort of machine learning algorithms to our input, and we get some output. We can have 1 or more hidden layers. If we have more than 1 hidden layer, then we have a deep neural network, and that's all that deep learning is. It's more than 1 hidden layer. It's not terribly sophisticated. We turn, let's say, a cat here, if we're doing image recognition, into a series of inputs. These could be, you know, grayscale items from black to white, and associate a weight to each of those. And then we start to apply those to each of the nodes in the next hidden layer. We'll start off by localizing this diagram to just one of those to simplify things, because everything else is the same thereafter. So we have a series of inputs and a weight on each of those arcs up to the first node in the hidden layer, the first hidden layer. So we're going to do our weighted sum, 2.5 times 0.8 plus 0.5 times 0.7 plus 1.3 times 0, etc., etc. But then we have this bias node. So earlier on I said that we could have parts of the network switched off, you know, with a score of 0 after we've applied the activation function. But to each node, essentially what we add is a bias node to make sure that the output cannot be 0. It's going to be some score or other. It could be a low score, but we don't want any parts of the network to be entirely switched off. So once we add that all up, we get a score of 2.7. We apply the sigmoid function to that. We can just look up, we go along the x-axis, find 2.7, go up to the graph, and then we just read off on the y-axis the value for 2.7, and we get 0.94. So that will be the output from that particular hidden unit, okay? And then we do the same for every single combination of calculations for all of the other hidden units up to the next hidden layer, to the output, and then we make a prediction. So our input was some vectorized version of a cat, and then we're trying to predict the label of that image. For example, we have 4 possibilities: a dog, a cat, an owl, and a lion. And if we pick cat because it has the largest value, then our neural network has successfully recognized that particular image as a cat. It's correctly classified the image as a cat.